Alright, let's get started with section 13.4, which is the probability of disjoint and overlapping events. So our objectives are to find probabilities of compound events, use more than one probability rule to solve real-life problems, and our essential question is how can you find probability of disjoint and overlapping events? Alright, to start, we've got some vocabulary. Let's make sure we understand our key vocabulary words. Compound events is the union or intersection of two events. Here's an example of a union of two events. So fill in your blank Venn diagram in your notes with the following example. Overlapping is when two events have one or more outcomes in common. Here's an example of an intersection that's overlapping, and they have one or more outcomes in common. That's this section right here. And then disjoint, another word we could also use is mutually exclusive, is when events have no outcomes in common. And you can see that the two circles are not connected or overlapping at all. These would be disjoint. So, core concept, probability of compound events. If A and B are any two events, then the probability of A or B is, and here's your notation, so probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. And then if A and B are disjoint events, then the probability of A or B is equal to the probability of A plus probability of B. Two formulas that you'll need to be able to use in today's lesson. Alright, so let's practice our two formulas. Example 1, finding the probability of disjoint events. A card is randomly selected from a standard deck of 52 playing cards. What's the probability that it is a 10 or a face card? Alright, so we can use our given Venn diagram. It's clearly a disjoint example. And also let's define our events. Let event A be selecting a 10, and then event B will be selecting a face card. So we can look at our examples here. We know that there are 4 possible 10s in a deck of cards. So our outcome for event A is 4. And then we know that there are 12 possible face cards. So our outcome for event B is 12. So when you're setting up your probability, we want probability of A or B. So that equals the probability of A plus the probability of B. So the probability of A is 4 out of 52 plus probability of B, which is 12 out of 52. Since we have a common denominator, we don't need to find a common denominator. We just add the top numbers. So the numerators add to be 16. Keep the denominator 52. Simplify always your fractions, which is 4/13, which converts to decimal 308. So the probability of a 10 or a face card is 4 out of 13 or decimal 308. Alright, example 2 is finding the probability of overlapping events. You have a card that's randomly selected from a standard deck of 52 playing cards. What's the probability that it is a face card or a spade? So first, let's define our events. Let event A be selecting a face card, and then define event B as selecting a spade. So when you look at your Venn diagram, we have all the face cards in circle A. All of our spades are in circle B. What's here in the middle in the overlapped section is the number of cards that are in common between the two events. So our total outcome for event A is going to be 12, and then our total outcome for event B is going to be 13, meaning we have 12 total cards. You have 3, 6, 9, plus these 3, 12. 12 for event A, and a total of 13 for event B. So what we have to account for is the overlap. And our overlapping outcome value is 3. That's these 3 spades that are also face cards. All right, so when we set up our probability, We want the probability of A or B, and that's going to be the sum of probability A plus the sum of probability B, and then subtract what they have in common, which is the probability of A and B. So those ratios are 12 out of 52 plus 13 out of 52 minus 3 out of 52. They all have the same denominator, so you just need to add across the top and subtract. So 22 out of 52. And that simplified completely is 11 out of 26, and then converted to decimal 423. So we have about a 42.3% chance of selecting a face card or a spade when we randomly choose from a deck of cards. All right, so now we want to use our formula to find the probability of A and B. Out of 200 students in a senior class, 113 students are either varsity athletes or on the honor roll. There are 74 seniors who are varsity athletes and 51 seniors who are the honor roll. What is the probability that a randomly selected senior is both a varsity athlete and on the honor roll? Well, this is a lot of information, so I think creating our own Venn diagram would be helpful in order to figure out the probability. So start by creating a Venn diagram. So the big picture is that we have a senior class that totals 200. And we have two different categories. We've got varsity athletes and we've got honor roll. Let's define event A as selecting a senior who is a varsity athlete. So our Venn diagram, the total is our senior class. So that means everybody in this circle plus everybody in this circle are a part of the senior class of 200. But A is a senior who's a varsity athlete. So this number 74 is just the number of senior athletes, which is given in our text. And then event B will be our selecting a senior who is on honor roll. And that number is 51, also given in the text. So 51 seniors who are on honor roll. We just don't know the number that's overlapping. We know there's a total of 200. We know there are 74 seniors who are athletes. We know that there are 51 seniors who are on honor roll. So we're trying to figure out the overlap here. Okay, so we know that the outcomes for event A is a total of 74. We know the outcomes for event B is 51. So our probability of A or B is going to be the probability of A plus the probability of B minus the overlap, which is the probability of A and B. So here's what we know that there's 113 that's going to equal the 74 plus the 51. No, sorry. It's what's given. So the 113 students are either varsity or on honor roll. So that's going to help us with some of the overlap. So we know that the probability of A or B is 113. So that's going to replace probability of A or B in the formula. And our total is 200 because that's the total senior class. So probability A is 74 out of 200. Probability B is 51 out of 200. What we don't know is how many is in this overlap in A and B. This is our question mark. So do our combining. So we end up adding this probability of A and B to this side. And then the 1/13 over 200 got subtracted to the other side. So we're just kind of flipping sides and following our order of operations. So now we have all our fractions on the same side with the same denominator, so you combine the numerators to be 12 out of 200. Simplify your fraction completely, always. So 3 out of 50 is the probability of A and B. So that's the question mark right here. It'll be 12 to fill our question mark. That's the overlapping number. So that is decimal 06. All right, our last example, we're going to use more than one probability rule, which is always a possibility. So you've learned about several probability rules. So in a real life situation, we could combine any of these rules to kind of help us answer questions about probability and statistics. So the American Diabetes Association estimates that 8.3% of people in the United States have diabetes. Suppose that a medical lab has developed a simple diagnostic test for diabetes that is 98% accurate for people who have the disease and 95% accurate for people who do not have it. The medical lab gives the test to a randomly selected person. So what's the probability that the diagnosis is correct? First, let's define our events. Let event A be the event A will be a person who has diabetes. Let event B be a person with the correct diagnosis. Note, the probability of B depends on the occurrence of A, so the events are dependent. So when A occurs, the probability of B is 0.98, and that's based on information that we're given here in the text. When A does not occur, probability of B is 0.95. All right, next we see that we can use a tree diagram. Probability tree diagrams can help us where the probabilities are given along the branches. So these are our branches as we move along the tree. And they can help us see the different ways to obtain a correct diagnosis, which is ultimately what we're looking for. And we're going to use complements of events A and B to complete the diagram, where A with the bar above it is a person that does not have diabetes, and then B with the bar above it, remember these are notations for the complements, would represent incorrect diagnosis. Notice that the probabilities for all branches from the same point must sum to 1. So let's start at the beginning of our tree. We know we're dealing with a population of the United States. Well, the probability of event A occurring is the person who has diabetes, remember, and the probability that of the complement of A would be a person that does not have diabetes. So either the person has diabetes or the person does not. So the complement, remember, notation is A with the bar above it. And then if the person has diabetes, they could either have a correct diagnosis, that's event B, or an incorrect diagnosis, which would be the complement. Or if they started out with not having diabetes, they could have a correct diagnosis, event B, or they could have an incorrect diagnosis, the complement of B. Now we need to fill in our percentages, or our decimal values. So the decimal value of a person having diabetes is 0.083. That's a value that was given in our text, right up here. Estimates that 8.3% of people in the United States have diabetes. So this is a number that was given, so we put it along this branch. So then we just need the complement of that value, which would be 0.917. So again, the complement would be to subtract this value from 1, and that will get you the 0.917. Next branch, correct diagnosis is 0.98, again given in the text. So the complement of 0.98 would be 0.02. And then our value for correct diagnosis was 0.95, also given in the text right here. And the complement would be 0.05. So to find the probability that the diagnosis is correct, follow the branches leading to event B. So for the probability of event B, it would equal the probability of A and B plus the probability of the complement of A and B. So we figure that out by getting the probability of A times the probability of B given A plus the probability of the complement of A times the probability of B given the complement of A. So plug in your values for all those different probabilities. So 0.083 times 0.98 plus 0.917 times 0.95. That comes out to be approximately 0.952. So we have a probability that the diagnosis is correct is about 0.952 or 95.2%. All right, that's all for today's lesson, and we will practice in class tomorrow. See you then.